Okay. Uh, Good morning, everyone. For today's presentation, the paper I introduced is called MOE-LoRA, which stands for a mixture of expert-based parameter efficient fine-tuning method for multitask medical applications. The outlines of this presentation will be as follows. First, a motivation behind the paper, then the abstract, then we will go through how we can apply the like large language model for medical applications, and the multitask fine-tuning, and the method MOE-LoRA, and finally the experimental results. So the motivation behind this paper, starting by as we know, recently the large language model gained a lot of attention due to its huge capabilities in different domains and applications. So one of these domains could be the healthcare systems, or using the web-based healthcare systems, which need to be customized large language model for it. So how we can benefit from using the large language model in such a domain, medical domain? First, it could be benefit for both the patients and the doctors. For the patient, it could be a very easy access to medical information, as we can use the large language model for an online chatbot. Also, a very easy or simple consultation. For the doctors, it could help for the disease diagnosis, especially in the clinical decision support systems, where the doctors use another support systems help them for the disease diagnosis. So how we can use or which is the challenges or the issues that can face us when we try to use the large language models for the medical domains. First, we have not just one or two tasks. We have a lot of medical tasks we need to apply for with different scenarios in the real world. So it could be as we said, a chatbot application, or doctor recommendation system, or the medical named entity recognition, a lot of different medical tasks. When we if we try to use for example, the multitask learning or fine-tuning just with this dataset, one dataset containing different tasks. For example, here we have the CPLU from dataset. This dataset has here 8 different tasks, and each task has different numbers of samples in the dataset. So when we try to fine-tuning the model with such a dataset, we can face some sort of imbalance or suboptimal fine-tuning due to the imbalance of the distribution of the dataset of each task samples in the training dataset. Also, if we want to apply a full fine-tuning for doing the multitask learning, the cost of the full fine-tuning is another issue we can face in this matter. So here comes a proposed method in this paper, where they tried using the multitask learning. One method is called mixture of experts. But if we use it alone, as I said, it could be has some sort of imbalance in the dataset distribution between the tasks. And for the full fine-tuning, for the full-time fine-tuning cost problem, they try use such as parameter efficient fine-tuning methods, such as LoRa, but usually like LoRa is using for only one task, like could not be used for a lot of tasks. So how we can fix this? They proposed MOELoRA, which tried to combine the two methods together. First, using the mixture of expert for the multitask learning for different tasks, and for the parameter efficient fine-tuning, they use LoRa, the low-rank adapters. So we will have multiple experts per task, which will be the trainable parameters only. And for each expert, it will be consist of the low rank matrices from the LoRa method. And to control the contribution of each expert, we will use a task motivated gate function for that. So next, we will talk about how we can use the large language model for medical applications. So usually like the medical task, or in general, like NLP downstream task, has each task has a consistent structure of input and output buttons. So for example, if we have a medical name entity recognition, we will have if we use traditional models like large language models, just not the large language model, the input will be a medical text, and the output will be expected to be the output head and the output tail, which we will determine the head and the tail of the entity. When we try to use a large language model for such an application or a task, the problem will be that the large language model usually expects the input and the output to be linguistic. So we need to restructure the task datasets to be compatible with the large language model structure. So we need to modify the input. For example, like here we will need to add some sort of instruction to guide the large language model, how it will need to deal with the medical text. Like, for example, please recognize the medical name entity in this sentence. And the output, instead of being just the head and the tail of the entity name, it will be formatted or structured to be a linguistic text. It will not like, it will be like, for example, the medical text has the following pairs of entities: head entity is, and the tail entity is. So for each dataset, or for each downstream task or medical task we need to apply using the large language model, first we need to restructure the input and the output. Then we use the large language model to fine-tuning with this modified dataset. So what if we want to use a large language model or fine-tune it for different medical tasks? So let us assume that we have a set of medical tasks, and for each medical task, we have a restructured dataset as here, compatible with the large language model format. So we need to optimize the parameters not only with across one dataset, one task dataset, but across all the dataset. So we need to find like some sort of conditional like language model objective function that could achieve this goal. So here they proposed this objective function, which they like iterate for different tasks, and for each task its dataset, and for each dataset the output will be in the probability will be in this format. which is be a conditional depend on like here it will be the probability of generating this is the current output token when we have the input sequence X and the prefix of the output sequence up to token T-1 before the current token generation generated YT. So that how we can optimize the large language model across the whole data set with different tasks. So next, let us go through the method of the mixture of experts. In this method, like we can see it as we have different like sub networks or networks. Each network will be trained on specific tasks in like, for example, expert 1 will be trained on subset 1 and has the highest performance across the all expert on it, and so on. So after we trained each expert on each data set, then we combine the whole output by regulating or by controlling the contribution of each expert output to the whole output using this gating function or network. So yeah, this is the general idea of it. The expert could be like any types of networks or subnetworks of the whole system. But in the original method, the expert first is being trained before training the gate parameter on regulating the contribution of the experts. But in the current paper, they train the expert at the same time with the gating network, as the expert is just part of the network, not being like explicit, like not like, for example, expert 1 for task 1 and so on. No, the contribution will be depend on the task, as we will see later. So next we will talk about the method itself, mixture of expert LoRa. Here in this method, as we usually, it is the same as LoRa, but the mix of expert layer, LoRa layer, will be integrated in each like for example, here we have in the linear layers and the attention layers. So, and as LoRa, the original pre-trained model will be frozen. So to train the model on the multiple different medical domains or dataset, we will need the task-motivated gate function. This task-motivated gate function will make sure that like each task, like for example, we have 8 tasks, each task will have a unique set of parameters from each expert. So also like for the gate function, instead of using different gate or individual gate function for each mixture of expert LoRa layer, they use just one gate function to control the whole network. So next we will talk about LoRa, the low-rank adapter fine-tuning method. This method was already explained previously by Pak Nugent Shi, and here we will just going overview of it. In LoRa, we have the large language model parameters being frozen, and we will use some sort of adapters. These adapters will be consist of two low rank matrices, and this the contribution of the adapters to the whole output will be controlled by the alpha constant, hyperparameter constant, which will control how much the rank matrices will be contributed to the whole output. So when we try to use mixture of expert with LoRa, we will, instead of using one like just two matrices, we will use for each expert will have its own two rank matrices, and for each expert we will define the weights, which will be the value of the gate function to control the contribute of each expert to the whole output. Okay. So even like we will define two low rank matrices for each expert, the number of the parameter will still be the same. How? Because each expert, the number of its parameter will be R, the rank over the number of the expert, um, multiplied by like the dimension of the input and the output. So when we combine the whole parameters, like for example, in LoRa, the whole parameter will be like for example here, the PA multiplication will be the dimension of the input by R and R by dimension of the output. So this will be the whole number of the parameters being trained. So in mixture of expert LoRa, the whole number of the parameters will be the number of expert by the rank over the number of the expert, which will be the amount of the trainable parameters of each expert. So we will end up with the same amount of the trainable parameters in LoRa. So we will not like have any additional fine-tuning cost using this method. So how the task-motivated gate work? As I said before, the task-motivated gate function is determine how much each expert contribute for the current output or for the current sample. So the input of the gate function will be the task identity, but the task identity will not be like depend on the sample, on the current sample, just as we already use as we are already use the data sets that have different tasks, and for each task like subsets, labeled subset for each task. So the gate function will just has the input the task identity from the dataset, and because like if it is a sample motivated gate function, it could like be more difficult to fine tune it because it's depend on each sample in the dataset. But by using this task identity, we will just like limit the inputs of the motivated gate function to just 8 different inputs. So the contribution of the weight vector omega j for each task tj will be expressed as a softmax value. So the sum of the whole contribution of the expert will be up to 1. And the weights for each task will be a summation of the model frozen parameters and the trainable parameters, which will be the sum of the each contribution per the expert, and the expert will be is consist of 2 low rank matrices. So next, we will go through the experimental results. First, for the fine-tuning, they use the chat GLM model, the 6 billion model. And for the trainable layers, they didn't inject the adapters over whole layers. They just injected in the, use it in the linear layers and self-attention layers. The dataset, as we said before, it will be prompt CPLU dataset, which is a Chinese multitask medical dataset. It contains 16 different medical tasks, but here they just use 8. To compare with other baselines, they compare it with large language model without fine-tuning, like ChatGPT. But as it is without fine-tuning, they use some sort of task descriptions and in-context example in the prompt. They also compare it to the large language model with fine-tuning, but they use different like fine-tuning strategies. First, they use a p-tuning strategy, which will, it is a prompt tuning method, like a soft prompt tuning method, where we add like some sort of continuous vector trainable parameter vectors in front of the input and train these parameters for the different tasks. And we will also see that they compare it to the pure LoRa method for evaluated over the cross-task generalization for different tasks. They evaluated on to LoRa Hub, which is a new or recently published method. This is the evaluation matrices. So for the experimental result comparing to the other baselines, first we can see like here we have the large language model without fine-tuning. Comparing to the others methods, the large language model without fine-tuning is like lag behind them, which we can here see how the fine-tuning is important to large language model if we want to apply it to SAS, like task-specific medical knowledge. But like also we can see ChatGPT has better performance than the other model, which go Wutu. I'm not sure. This because like even with using the in-context learning with larger models will like have better performance than the smaller models. For the fine-tuned models, we have LoRa full, like it is being fine-tuned with using the full data set, and LoRa models that is being like fine-tuned for each data task data set individually. Like here we have one model, here we have 8 models one for each task. And here they use the LoRa on the whole data set, but with some sort of task description in the prompt. Yeah. So for the comparing to the fine-tuned models, we can see the like LoRa based models here is like outperforms the prompt tuning model strategy, which like because like LoRa already outperforms on the other tasks, and LoRa full has better performance than like if we fine-tune using the whole dataset. It is better than fine-tuning it on a single dataset, like which we can ensure here's a generalization or over the different tasks. And comparing to the LoRa hub, the performance wasn't that good because like in this introduced method, they said that they need a vast or a huge amount of data set to fine-tune the models, which is not the case in this paper. So we can see using this mixture of expert LoRa method outperforms almost over the others baselines. And in the second table, they compare between the contribution of each component of mixture of expert LoRa itself. So first of all, they try to compare the model without using the mixture of expert method. So we can see this is just LoRa. The second one, they try to remove the gate function using the mixture of expert method, but without the gate function. And the third one, instead of using one gate, instead of using one gate function for the whole data layers, they use different gate function for each data layer. But the performance of this combination is good, but it is like need a lot of more additional parameter to be trained. Finally, they also try different combination of the patch samples dataset. So for the patch, first they try to use the same task samples in each patch, like for example, named entity patch and so on, and train the model. And the second one, they try to use it randomly from different tasks. But the introduced combination in this paper out almost like have the better performance, even like the others could have some sort of better performance alone, but it is just on specific tasks. The average performance of mixture of expert LoRa was better than the others. So finally, we will they try to do some analysis on how much each expert contribute to different tasks. So we have different tasks, 8 tasks, 8 experts, and here they just select 4 tasks to see how much each expert contribute for each one. So we can see like there's a significant variation in contribution between each task from each expert from for each task. So this could be like show how each task has a unique set of parameters like defined for each task. And some tasks like here has like some expert contribute like large amount compared to the others in specific task, which like we can see, like for example here, expert 5 and expert 3 like gain a lot of parameter contribution to these tasks, and like the similarity of the using like we can see like the amount of each expert contribute to different tasks could explain or leverage how much when we can benefit from multitask fine-tuning over different related tasks. But maybe if the tasks is not just like a medical task in the medical domain, it could be like we can see a very difference in how much is expert we relate to each task, not like this. Yeah. This is the end of my presentation, and I would like to answer any questions if there is any.
Okay, so Maab, I didn't get it at the beginning, but what was the problem with just using LoRa without mixture of experts?
LoRa without mixture of expert will not be like, because we have different distribution for each task in the whole data set. If we used just LoRa with the whole data set, the performance will have like sometimes imbalance or be biased according to the number of the samples of the task. Like for example, this task has a large number than the others, so the model could learn this task better than the others.
Oh, okay. So for the tasks that have small data, if you train it on the whole data set with all the different data sets, then it will not perform as good on the tasks that have a small data set. That's the problem. Is that the problem?
Yeah.
Okay. Um, so in the last table, showing the performance, where it says LoRa, the ones that says LoRa full and single. So basically, how they're training it is they're just using one BA matrix, and they're just training that same matrix over and over again with all the different data sets. Is that correct?
Yeah.
And then so the difference between MOE-LoRa is MOE-LoRa, it will have a different separate set of BA matrices for each task, but it will use the same like so there will be the original weights that are frozen, and that is the same set of weights. Like there's only one set of weights that for the original model, and then you have like let's say n different BA matrices, and it's just the n different BA matrices that you're training for MOE, and you're selecting between the BA matrices. Is that correct?
We don't select between them. We apply this gate function that will determine how much each PA matrices is important to the current output.
Oh, okay, so it's like a weighted sum of the different BA matrices.
Yes.
So every time a user puts in a query, when it's making a response, it'll use small parts of every single of all the different BA matrices, depending on how important they are.
Yeah, this is exactly how it is
Okay,
explained here.
okay, I see. So also when you show the results, I think there's a different page that shows like they're using ChatGLM as the yeah. So is there a reason they use that model? Is it like a Chinese language model or?
Yeah. They said that this model has better ability to understand the Chinese language.
Oh, okay, so it's like it's a language model trained on Chinese text, like specialized for Chinese.
I'm not sure if it is specialized for Chinese, but they said it is the best model to interpret Chinese data sets.
Okay, so I mean, so this paper is basically like it's focused on Chinese language, right? Like the tasks and the data sets, they're all Chinese, right?
Yeah, but
Oh,
maybe like it could be like used for another models. Just that because the data set is Chinese, so the
mhm.
model could be need to be deal with Chinese data set.
Okay, I see. Um, Going back to the performance, it looks like there's not much difference in the performance of mixture of experts and just using LoRa. So there's
Yeah.
only like 1 point difference. So, but it seems like mixture of experts is a lot more complicated to train than LoRa, right?
Mm,
Like, it requires n more, like times n ma more ma different matrices. Then you have to train the gating model. It seems like a much more complicated process.
it is the same number of
Like it's the same number of total like parameters because you're
yeah.
dividing by n. Um, but the process, I mean, because you're training that many different matrices, and then you have to also train the gating mechanism, right?
Mm,
So it seems like a more complicated process, but the performance is only 1 point difference.
yes.
So if like for us, like if mm, yeah, uh, it's so I mean, so is this something that you feel like you you intend to further develop in terms of like using the
Yeah.
mixture of experts? Yeah. Uh-huh.
Even like maybe the difference is not that huge, but I
Hmm.
thought this method could be like a good start point to start from, like
Hmm.
um,
Okay.
the idea of using different experts for different tasks.
Hmm.
I thought it could be like benefit maybe with more improvement.
Okay. So even though right now it's not a big difference, with more development, maybe we can increase the performance even further. And
Yes.
from okay, so that's the idea. I see. Um, yeah, I just have more questions about overfitting and underfitting, but I think maybe after. Uh, yeah, because the papers that I've been reading, they address the problem with when you use regular fine tuning, there causes overfitting, underfitting problems. So I'm curious about that, but maybe we can talk about that later. Um,
Okay.
yeah. Okay. Thank you.
Thank you.
Maab,
Okay. Yes, Professor.
in this paper, there are gate weight and LoRa weight. Do they
Yeah.
learn the two weights simultaneous or step by step?
Mm. Yeah, there's two weights, the gate weight and the LoRa weights.
Um, how long these two weights simultaneous or step by step?
Uh, yeah, at the same time. Yeah, science
Same time?
simultaneous. Yeah, it is different from the original mixture of expert method because usually they train the expert first, then train the gating model in the second step. But here, they train them at the same time.
Two component weights on at the same time?
Yes.
Okay, yeah, I see.
Okay. Uh, if there is no more questions, I will end my presentation for today. Thank you. 네, 감사합니다.